Hey everyone, hope we're all going well. Now, I just wanted to start today with a reminder about Math Space. Now, if you've been looking on the Connect page, you will have seen that Math Space is one of the tools that we're starting to use. And I think it's a nice little and quite a robust little tool, a robust little website that lets you fiddle around with stuff a bit. You can ask it for answers and extra help and things like that as you go. It's got built-in textbooks to help you out just with covering the content we're going to be doing. Now, if you go on to Connect, you'll see the access key to get to join up to the class. And I'm going to be semi-regularly assigning content through MathSpace that I think will benefit you for doing some of your own revision in your own time at home, and especially at the moment when we're doing a lot of working from home. Okay, so just going to get going with today's lesson there. So today we are looking at function transformations, and you may be vaguely familiar with these from when you've worked with quadratics and parabolas. But we're just sort of looking at it in terms of general functions. We touched on this yesterday as well, so you'll have a bit of an idea of what's going on with it. But basically, it's looking at how the position of and shape of certain graphs change as we change certain things about them. So, just a moment. So what we've got here is a bit of a summary of 4 of the main types of transformations that can take place. Now, I'm actually going to go down to these ones first because these will be the ones that you're probably much more familiar with, especially when you're working with quadratics. So with quadratics, you could shift your graph up or down by simply adding a number onto the end of it. And we see that here where we've got our parabola that if we add a number to it, it just shifts the whole thing up by 3. This makes sense if we think about what we're actually doing. If we substitute a value of x into here, if we were to compare y equals x squared to y equals x squared plus 3, this second graph is always going to be 3 higher up than the y equals x squared one. So we're all pretty familiar with that, hopefully, and there's a little diagram of how that moves up. Now, this one we may be a little less familiar with. Oh, actually, this one is something that we've seen a lot of as well. So this is when we have our x minus b inside the brackets. So this was when it was outside the brackets, just tacked onto the end. And this is when it's inside the brackets. And when we subtract a number, it actually shifts to the right. And this is the counterintuitive sort of bit, because we expect when we subtract, we would go to the left because that's the negative direction. But it's when we add that we actually go to the left. So this graph here is one of y equals x take 3 all squared, and that's been shifted to the right by 3. This one is one of x plus 2, that's been shifted to the left by 2. And this matches up with what we've already done on when we're looking at where the x-intercept of a parabola is, or the x-intercept of values are. We already look at what x needs to be for the whole thing to be equal to 0 inside the brackets by the zero index law, or zero product law rather, and so that's something we should be fairly familiar with. Now, the other one we've got is this multiplying by a certain amount. So if we multiply our parabola by a number, so we've got ax squared, that stretches it vertically. So here we've got, we multiply it by 2, basically goes up twice as quickly. We multiply it by a quarter or divide it by 4, it goes up at a quarter of the speed. So that's one we should be fairly used to as well. Yeah, so, the other one we've got is if we happen to have a negative number in the front, it's literally just reflected, and we say reflected in the x-axis, and that means that it just sort of is this vertical reflection. Now, there are in fact two more of these that are interesting to have a look at, and in fact I'm going to look at these in terms of general functions of what they are. And when we've got a general function, we actually have it in the form of f of x. And certain things that happen with our f of x is we could do f of x, and I'm going to do f of x take, how to just take b in the example, and that would shift to the right. We had the f of x plus c. Now this is not using the x squared term anymore. This is using f of x. So this is the case for any function. This is going to be a shift upwards. We had our a of f of x. And this is called, or shift upwards by c, shift to the right by b. This one does our shift, or not really a shift actually, what's the word they use? It's a dilation, that's right. So we would say this dilates by a factor of a. Now there are a few more, but we're not going to deal with those just yet. But the other ones that we might want to deal with, and I'll write them in green over here, is this is when we've got our number being multiplied outside the bracket. Sometimes we'll get one where the number being multiplied is inside the bracket. So that will be f of dx. This one is probably the hardest one. Then that actually basically squishes it in vertically. So the higher this number is, the more compact it ends up getting. And so we also, and I think that's it. Yeah. So it's basically we add or subtract inside the brackets, or we multiply inside or outside the brackets, and each of these will end up doing a different thing. We also had negative f of x, and that flips vertically. And then we have f of negative x, and this one is a bit counterintuitive. This one flips horizontally. Now, these two ones we don't have to worry about so much, because this one is, I forget the exact word that was used to describe this, but basically what this would mean is that a graph that was originally like this, if multiplied by dx, would start to be compressed in, and it would sort of be squished in, basically. But when we actually cover that topic, I'll be talking about that in a little bit more detail. But that's a really interesting one, definitely. So, there's some other terminology, and in fact, let's get the actual terminology. These are called translations. So the translation is when you shift it to the left or right, and this is a dilation when we basically stretch it up or down. So, and then it would be by a factor of a. So you could say it dilates. When we look at these ones up here, we would say that this one here dilates by a factor of 2, and this one dilates by a factor of a quarter, is how we would say that in the correct terminology. And then our other one that we've got, this one here, is what we call a reflection. And we have to be careful about how we call it. It's a reflection in the x-axis. So we imagine that the x-axis is itself a mirror and it's being flipped to the other side of the x-axis. So where have we got that there? Yep, reflected in the x-axis. So this is just some of the terminology we can use when talking about these things. Now, when we are, there's some other terminology that we have to be using when we're talking about graphs. Some of these we'll be familiar with. When looking at a graph, it'll have x-axis intercepts, and we've got those, they're pretty straightforward on this graph, A, B, and C. And we've got a y-axis intercept. Hopefully we're all pretty comfortable with dealing with those. We've got our turning points as well, and depending on our graph, we'll have a different number of turning points. In your typical parabola, you'll have one. In your typical cubic, you will either have 0 or 2 turning points. Here we've got 2 turning points. And we have to define our turning points. E is called a maximum turning point because it's the highest value that it gets to, that's the maximum. And F is called a minimum turning point because it's the minimum that it's getting to. Got to be careful with what we think, because this isn't the minimum across the entire function. This is actually what we call a local minimum. Because it's pretty clear that if we were to look across the entire range of x values, that as we go to larger negative x values, this one will get far lower than f is, and this one is already, up here, is already clearly higher. This one down here will get lower, this one up here will get higher, and it's already clearly, this one does clearly get higher than E. So sometimes we end up calling it a local minimum instead, but it's a minimum or a local maximum, but they're also called maximum turning points or minimum turning points. Now, another bit of terminology is when we say something is concave down. Concave down means that it's pointing downwards, the points are going downwards. A maximum turning point is concave down. So, in fact, I'll draw this in green line on the diagram. But basically, all of this section is called concave down because it is pointing down. And then we've got the next section, which is concave up. So concave up is where it's pointing up. So if things are looking up, then you're smiling. So we've got a smile there. And if things are looking down, unfortunately, you're frowning. So that's why we've got a frowny sort of thing there. That's a little way we can think about it. And then it refers to this point G. And it says that it appears to be concave up to the right of point G, and it's concave down to the left of point G. Does point G have a special name? And yes, point G does have a special name. The special name that we use for point G is the point of inflection. So a point of inflection is the point at which it stops being concave down and turns into being concave up, or the other way around, stops being concave up, starts being concave down. And when we get into calculus, you will find out how we actually determine mathematically what the exact point of inflection is, but that's a bit further down the line, so we don't need to worry about that. At the moment, we're just sort of looking at it and going and being able to identify roughly where we think the point of inflection is just by looking at it more than anything. Okay, so if we are looking at, the point where it changes is called the point of inflection. Now here we've got a concave down. As an example, we've got concave down and then it transitions into being concave up. So it's going down, then it starts turning around and coming back up again. And then we've got our point of inflection in the middle. And there's also something called, now if it just so happens that our inflection is perfectly horizontal, it is called a horizontal inflection. And that happens typically with our standard cubic, x to the power of 3. Because if I was to graph x to the power of 3, And let's just put that there. It does end up being, and I can zoom in on that, it does end up being perfectly horizontal right there in the middle there. So that is called a point of horizontal inflection. Again, when we get to calculus, we'll be able to determine exactly what is a horizontal inflection, but obviously it's where the gradient would be 0, so it's a flat point there. Okay, so with some of that terminology under our belt, we should be able to start looking at some of our graphs and working out exactly when something is concave down, where it is concave up, and I'll see if I can get the same colors here because it's always good to have the same colors. What colors did I use? The intercepts were in yellow. No, it's not really interested in the intercepts. And turning points in green. And the point of inflection in orange. So let's have a look. Where are our maximum turning points? So that's going to be a maximum because it reaches a maximum there. We've got another maximum up there. So these are our two maximums. Now, where's our minimum turning point? We've got a minimum down there. Where are our 4 points of inflection? Well, pretty much they're points where we haven't got, where we're transitioning from curving down to curving back up again. We've got one there, one there. This is an interesting one. It sort of goes from curving down to curving back up and then goes back to curving down again. So these are our 4 points of inflection. And only one of them is horizontal, and appropriately enough, it's called the one that's labeled with H. So we've got our horizontal inflection right there. So between which points is, in fact, I'll use my highlighters instead here just because it makes it a bit easier. Where is it concave up and where is it concave down? So it always transitions between concave up and concave down at a point of inflection. So this is a frowny face, so it's pointing down. Then it will go into concave up. Then it changes back again into concave down. And then very briefly, even though it doesn't actually get to a turning point, it does turn to concave up again, and then it goes back down to concave down. So that's the one we've got there, and that's how we can illustrate our, that's how we can define what we've got there. So you're welcome to practice some of these, and you can. This one here asks us to sketch the graph on our graphics calculator, and we want to determine all of these points. I'll actually do that here. You're welcome to give it a shot yourself, but if I put it in my graphics calculator is actually able to find all of these points with using various graphic analysis tools, and I'm just going to show us how we can do that. Here we are. So that is my equation. I'll put that in there. And let's get ourselves a range that is going to be a bit more useful. I'm going to put it on default first just to see what it does. Looks like I need to zoom out a little more. And in fact, let's change some of our things. So it looks like our X-min and X-max. I'm going to start that, go from, I think, -10 is as far as we need to go negative, and maybe out to 30 just to see what it looks like. Let's see what that looks like. Probably a bit too far, so I'm going to change that again. So -5 and 15. So that should give us a good horizontal range. Yeah, that looks pretty good to me. Not perfect. In fact, we can probably get even closer than that. -2 and 8. There we go. That looks much better. Then we can change our vertical range. Looks like I'm going to change my maximum to, let's try 15 and -15. And we'll do that one more time. Oh, there we go. So I've zoomed out a little more. So now you can always click this 4 arrows symbol to determine your boundaries. So in fact, I'm going to zoom in and I'm going to just change it a tiny bit more. Negative 15 is fine. I'm going to go to 20 up there. There we are. So that's looking pretty good. So if I go to analysis, I can actually find all of the points that I'm interested in. So let's find, now the special word for the x-intercept is root. It's got the y-intercept, so we'll just throw that in there. The y-intercept is at 0 and 10, so I'm going to write that in there. 0, 10 for our y-intercept. In GSolve, we can have a look at these. We'll look at our two roots, and so our roots are, and it's a little hard to see that, but it's negative 0.505. So it's negative 0.505, comma 0, because that'll always be 0. And I can just push left and right on my calculator to get to the next one. 3.0, is that 6 or 8? I'm going to assume it's 8 just for the time being. So that's going to be 3.08, comma 0 for C. And our last one will be 6.42. Comma 0 for our last root there. We can also find our minimum and maximum. So it does find our local minimum and local maximum. Here we've got 5, comma, negative 15. Remember to do your negatives. It's easy to forget those when you're looking at these. And then we do the GSolve for the maximum there, and that's 117. Fortunately, these numbers are a little cleaner than the ones for the x-intercepts. Now we can actually mathematically, or use the GSolve function to find the inflection points as well. If I do that, and it's found one there, fortunately they've given us inflections that are clean numbers. So there's 3, 1. And there was another one. Is there another one? No, that's it. So there's just the one inflection point. So now we've discovered all of the points there on our graph. And we did it just by sketching it. And after we sketched it, we were able to see exactly where all those points turned up. This is a really good skill to have. If you can do this kind of stuff quickly and efficiently during an exam, then you'll be in a really good spot for getting those exam questions correct. I'm just going to finish off by looking at this question 13 here. I quite like this one. It's one where we're looking back at what we had earlier on, where we were looking at the different ways we could be translated. So this is a dilation when it's stretched up or down, a reflection when we've got a negative value in there, and a vertical translation when we just add a number on the end, and a horizontal translation when we've got the number inside the brackets. So what we can do here is what we've got to work out is we've got to work out from these equations which ones match to which graphs, and after we've worked out which ones match to which graphs, we want to work out the unknown values for the coordinates or the unknown values in the equations here. So one of the things that I like to do when doing this kind of question is I like to just mark out what kind of graphs we've got in each case. So if you want to have a look at that, I strongly recommend you give this a shot before you just get shown the answers. So if you want to pause this and have a look at these questions, then I strongly encourage you to do that. That is all the equations and the first lot of answers, and first lot of graphs, and then we've got the second lot of graphs. So feel free to pause it and have a bit of a look, and then I'm going to solve it in just a second. So for this one here, actually we'll just go through the graphs first. What kind of graphs have we got? This one here is going to be a cubic. This is a quadratic or parabola. This is a square root function, because we've covered all these yesterday. and today, and indeed previously. This is our reciprocal. We've got another cubic, another quadratic, a quadratic. Here we've got a straight line, so I'm just going to say it's linear. And then we've got another reciprocal. There we go. So this should help us narrow down exactly what we're looking at. So first up, x cubed plus 8. This is a cubic, so we're going to look down and see which cubics it could be. So x cubed plus 8 can only really be, well, it's going to be this cubic, or it's going to be this cubic down here. Now x cubed plus 8, I would expect that to be centered around the vertical axis. So that would be, or the y-axis, that would be this one here. So I would expect a equals 8. And then we want to find where this hits the x-axis, which is where y equals 0. So we want to find 0 equals x cubed plus 8, or where does x cubed equal negative 8? X cubed equals negative 8 when x is equal to negative 2. So b is going to be negative 2. So that's our first one. Let's have a look at this one. Now this is another cubic. This is obviously our one down here. This is exactly the same as the previous one, except it has also been shifted to the left by 1. So everything else should pretty much be the same. Because we know it's exactly the same, but it's been shifted to the left, that gives us this one already, f equals negative 3, because it's been shifted by the left. That's what plus 1 inside the brackets means. We can evaluate if x is 0, then we've got 1 cubed, which is 1, plus 8. So g is going to be equal to 9. And there we have it. So that's our first two. This one here is a quadratic, and we don't know which quadratic it is. There are a few. Now x take d all squared plus e. It's just been shifted in some way. We don't know where it's been shifted, so let's have a look at some of the other ones first. In fact, I'm going to go straight for one of the other quadratics. X squared plus 4. This one should be pretty easy to identify. It's going to be one that's just been vertically shifted. Here it is, x squared plus 4, and quite straightforwardly, h is equal to 4. Not hard at all, that one. So that one's taken care of. Where is our other one? Okay, so we've got one here. I'm going to do this one in yellow as well. So this is our next one. Now that one is going to be, it's been dilated and it's been shifted to the right. So I look down here. This one looks like it's been dilated and shifted to the right. How much has it been shifted to the right? It's been shifted to the right by 4. So let's go back up to it. So it's been shifted to the right by 4. So it'll be b brackets x take 4 all squared. But what happens when x is equal to 0? If x is equal to 0, then what we would end up having is we'd have, this is going to be the y-intercept, negative 4 squared is 16. So 16b, y is going to be 16b. What is the y-intercept? The y-intercept is 8. So what's happened here is it's actually being multiplied by a half or divided by 2. So b is going to be a half because it's been reduced in size, it's been cut down. Okay, that's that one. Let's have a look. We have one square root function, so let's just get that one out of the way. X plus a, that means it's been shifted to the left. How far has it been shifted to the left? It's been shifted to the left by 4. So a here is equal to 4. And what happens when x is equal to 0? Square root of 4 is 2, so d is going to be just 2. There we go. So a few left. This is this is one of our reciprocals, and it has been dilated and then shifted down by 2. So let's look for one that it's not going to be this one that's been shifted to the right. It's going to be one that's just been shifted down. Here we go. So it's been shifted down by 2. What color did I do for that one? There it is, red, pink rather. So this one's been shifted down by 2, but where's that point? The equation for this one was y equals 8 on x take 2, if I recall. Let's have a look back up there. Where is it? Yep, 8 on x. Oh, I did blue, not pink. 8 on x plus 2, or take 2. So what happens when y equals 0? That's going to be 8 on x. So if that's 0 in there, we add 2 to both sides. 8 on x equals 2. 2x is equal to 8x. 8 divided by 2, so we end up with x equals 4 for that one. So I here is going to be equal to 4. Almost done. This one has been shifted to the right by f and up or down by g. Let's have a look at it. There it is. It's been shifted to the right by 1 and up by, it looks like it's been shifted up by 3. So if it's been shifted up by 3, then g is going to be equal to 3 and f is equal to 1. If that's the case, what point is e at? So that's y is equal to 1 on x take 1 plus 3. So where's that going to be 0? That's going to be 0 equals 1 on x take 1 plus 3. So basically negative 3, does that sound right? Let's see if we can solve this one. I multiply that across, negative 3 x take 1 equals 1, negative 3x plus 3 equals 1, take 3 off that one, negative 3x equals negative 2. They're both negative, so we can cancel out those negatives. X equals 2 on 3. That does look about right. This looks about 2/3 of the way between 0 and 1 there. So 2/3 seems like a good answer to me. So E is equal to 2/3. Now, I'd had to do a bit of maths to work that one out, but we are studying maths after all, so it shouldn't be too big a surprise. So that's that one there. That's probably the hardest one we're going to do in this whole set. But the last one is just back to our linear equations. What is the y-intercept and gradient? The y-intercept is 3. What is the gradient? The rise is negative 3 and the run is 6. So it's going to be negative 3 on 6, which is negative a half, or negative x on 2 plus 3. And so that's all those ones solved. This one did require a bit of extra work to solve, but we can do it all the same. So I quite like this one. It's a good little, just a second, it is asking for the coordinates here. I just did the values. It is good to just make sure we're doing the full coordinates, not just writing what the numbers are, because, but they are all on axes, so we can work out what that number would end up being. But technically, I should have been writing for D, it was 2, 0, for example. Sorry, wrong way around, 0, 2. This is exactly why we want to practice it, so we don't end up making those sorts of mistakes. Okay, So there's that one. This is a great little one. I hope you gave it a shot before being shown the answers. Yeah, hope you enjoyed that. Have a good weekend, and I will see you all on Monday. Have a great day.